If there is one thing I took from the global pandemic, it was a new view on hand washing. Our lives changed completely for months with lockdowns, face masks, one-way systems, but it was the frequent hand washing that made me realize how little I did before COVID. How disgusting! It now seems that our new, more frequent hand washing may even be reducing the number of colds and the spread of influenza we see. But why is that? What are we doing when we wash our hands that could stop the spread, kill the virus? It's that 5,000-year-old chemical that can get rid of grease, stains, muck, or even nasty microorganisms. Let's clean up that part of higher chemistry. This is Thing 4. Soaps have been an essential part of societies all over the globe and across the ages to keep utensils, clothing, surfaces, basically anything clean. Soaps are basically salts produced from the alkaline hydrolysis of edible fats and oils. This reaction means that the addition of a hydroxyl ion to the esters present in fats and oils. The OH will come from an alkali solution such as sodium hydroxide, NaOH. Natural oils found in the surrounding nature were historically used. Savon de Marseille, Marseille soap, in the south of France, is produced using the abundant regional products such as olive oil. The products of this reaction will be 1 glycerol and 3 fatty acid molecules. These last ones will be charged negatively and neutralized by the alkali present in the solution, sodium in our example, to form water-soluble ionic salts that we call soap. Their odd shape with an head and a long tail give the soaps their amazing properties. They will be able to dissolve in water at their charged ionic head, making them hydrophilic. And they will also be able to dissolve non-polar substances thanks to their non-polar tail, making them hydrophobic as well. Hydrophilic at one end, hydrophobic at the other, this duality will allow soap to dissolve oils, grease, fats with their tails while their heads stay in water. A little bit of shaking or brushing or tumbling and little spheres of grease surrounded with soap molecules will be able to detach. Because of the negatively charged head on the outside of this tiny sphere, they will repel each other and stay suspended in water. Bam! It's washed. Ah, that would be too easy. Water is rarely just water. There are always metal ions like calcium, magnesium, etc. dissolved in tap water. Check for yourself. Have a look at the back of any water bottle and you'll see a list of ions present. When there is a high concentration of metal ions, we say the water is hard. In this situation, soap and these dissolved metals will be able to form an insoluble precipitate called scum. Have you ever wondered why it was easier or harder to wash your hair in different parts of the country? Water is especially hard in the southeast of England. But do not despair, Londonians. There are also soapless detergents. Like regular soap, they have a nonpolar hydrophobic tail and an ionic hydrophilic head. They work the same way to remove grease and oil, but they are not fatty acids, and they have the advantage of not forming scum in hard water. And of course, both types of soap will help us solve our virus problem. The membrane in a virus is called a lipid membrane. Lipid means fat, so soap will annihilate the virus membranes like it was a simple stain to eliminate. So now you know everything about soap. There's a good reason we have been using it for so long and why it is far preferable to antibacterial wipes and gels. Knowing about soap will also hopefully help you give you a clean bill of health when it comes to higher chemistry. This was Thing 4. Thanks for watching.